and I'm going to take a sample in this stainless steel canister. I have snow in the chamber, and then I will analyze it for a suite of hydrocarbons when I get back to California.
And then this brown is the NO concentration in parts per trillion.
So this is our NO flow. So there's a pump inside here and it goes up and it tells you how much air is flowing through the tube. And then I write it down in my lab book every day.
NO in snow. Well, it's kind of a recent development that there's even NO up here. It comes from cars. Well, like basically that's where, if you're living in the city, there's a lot of NO produced from cars, and so it's kind of odd that it would be up here. And it's actually, somehow it's coming up here through the atmosphere, and it's almost getting snowed down in acid snow, kind of. I mean, a very small amount, obviously, but so it's kind of an art measuring it up here because it's so small, the amount of NO that we're seeing.
Sunlight has a lot of energy, especially in the UV. The ultraviolet rays are stronger than the visible rays. They have more energy. And it's a very unusual reaction that really caught us by surprise. This instrument here is, we call it the snowbird, but it's a spectroradiometer. It measures the intensity of sunlight at different depths. And there's fiber optic cables going into 5 different depths in the snow, and every 30 seconds I sample a different fiber, sampling a different depth. And it's amazing how quickly the sunlight drops off with depth in the snow. So just in the top few centimeters, there's a lot of chemistry going on. The sunlight releases trace amounts of NO. NO is something that comes from cars and smokestacks, electric power plants, and it creates ozone. These compounds that destroy the ozone layer are halogens. Those are man-made compounds, but there's also some natural halogens that come from the ocean. Table salt, the chloride, sodium chloride in salt, the chloride is a halogen. So we're looking at chloride, bromide, and iodine are the big halogens that are playing a role. In particular, the satellites tell us that there's very trace amounts of BRO, bromine monoxide, everywhere in the upper atmosphere, and we're not sure if the satellites are right, but that might be the source of bromine here to Summit.
So our first good sign today is that the box is upright and has not blown over. And looks to be still there. See, normally I would like to sprint back and forth because it keeps me warm. Well, I guess why am I not? All right, let's go. All right. Gases, which are undergoing photochemistry and other processes that we're interested in, can be lost out of the atmosphere onto particles.
So what we have here is a differential optical absorption spectrometer. That's what we call this instrument. And what we do is we send light from a lamp. It's very similar to the lamps that are used in movie projectors. We take this light, put it into a telescope, similar to astronomical telescope, make a parallel beam of light and send it into the atmosphere. At the end of the beam there is a reflector or ray which throws the light exactly back where it comes from, and then aim it onto the other side of the telescope and put it into a spectrometer and then analyze how the trace gases we're interested, for example bromine oxide, changes the spectrum. So in simple words, how it changes the color of the light. And by looking at the color we can identify the compound. We can also quantify the levels of these compounds in the atmosphere. So we believe we have seen these bromine compounds here in the air in Greenland. The next big question now is, where do they actually come from? Are they blown up here with the wind from lower altitudes from the ocean, or are they transported above us and then are transported down to the snow? And this is one of the big questions we still need to answer. Another data is
We're trying to really determine whether tropospheric chemists have overlooked the importance of halogens on a global scale.
That's what we're looking at, is these processes, these fundamental processes in atmospheric chemistry, and using real, going out and measuring what's happening and then trying to understand the process, and then this is what needs to be incorporated into these models.
By showing that these halogen compounds are actually present in the atmosphere here, we hope to improve the models that we use to predict the concentrations of ozone in the atmosphere, and that will hopefully help us to predict the future composition of the atmosphere.
I think just the fact that we know that NO is coming out of the snow and it's reacting with a ton of elements, as you're figuring out, basically, like, this could change our idea of models that people have been making, based on ice core samples. And so basically, our idea of what the atmosphere was like 1,000 years ago might change, because all of a sudden, wait, there's less NO or there's more NO than we thought there was.
The air and the snow here just tell you how we're all on this one small planet. It's possible that events almost anywhere on the globe could be recorded in summer.